A distillation system is designed to operate within certain predetermined limits. But when problems occur, efficiency and product quality can suffer. Operating a distillation system involves maintaining an equilibrium or balance between the rising vapor and the falling liquid in the column. One aspect of operation that can affect this balance is the system's feed rate. The feed rate is the rate at which feed mixture is pumped to a column. The flow of feed to a column can affect the quantity and quality of overhead product and bottoms product. For that reason, an optimum feed rate is normally determined mathematically based on system equipment and the materials being processed. An optimum feed rate is often determined when a system is designed and may be modified according to the mixture being distilled. However, a range within which the system functions efficiently is usually specified as well. For example, a system may have an optimum feed rate of 100 gallons per minute and an operating range of 80 to 120 gallons per minute. The way the feed rate is kept within the specified range depends on the system. In this system, a flow controller compares the rate of flow in the feed line to a preset value. If the feed rate needs to be adjusted, the controller signals a control valve to open or close. A distillation system functions most efficiently when its feed rate is kept within an established range. When the feed rate is regulated by a flow controller, slight variations in the rate can be expected. However, large variations can greatly affect a column's performance. If a system's feed rate is too high, overloading can occur. Overloading is a condition in which the vapor rising up a column is impeded by the liquid flowing down the column. For example, if the feed rate for this trade column is too high, the liquid will back up in the downcomers and build up on the trays. The increase in hydrostatic pressure restricts the vapor rising through the liquid. If overloading continues, more and more liquid backs up, and the rising vapor becomes severely blocked. This condition is known as flooding. While excessive liquid flow from a higher than normal feed rate is one cause of flooding, there are other causes. For example, a higher than normal reflux rate can have the same basic effect. Reflux is condensed overhead product that's pumped back to the top of a column. If there's too much reflux, the level of liquid on the trays can rise, increasing the hydrostatic pressure of the liquid and restricting or blocking the rising vapor. A column can also overload or flood if the temperature of the reflux is too low. A very low reflux temperature can cause too much vapor to condense in the column, which can overload the trays and impede the rising vapor. Excessive liquid flow down a column can cause overloading and flooding, but trays can also become overloaded because of excessive vapor flow up the column. One of the most common causes of excessive vapor flow is too high a temperature in the bottom of the column. If the temperature in the bottom of the column is too high, too much liquid is vaporized, and the vapor flow rate up the column increases. The increased vapor flow forces liquid up the column, flooding trays in an upward progression. If the problem continues, the pressure of the impeded vapor can increase to a point where it forces liquid out of the top of the column. This condition is sometimes called puking. When the vapor pressure is relieved, liquid flows back down the column, and the pressure buildup begins again. The surging of liquid up and down a column can sometimes damage internal structures of the column. Besides the causes we've described, overloading and flooding can also occur when vapor and liquid flows become restricted by scale buildup or damage to bubble caps or packing. But regardless of the cause, operators must be able to identify the problem so that it can be eliminated. A number of indicators can be used to identify overloading or flooding, including column pressures and temperatures. The buildup of liquid can cause the pressure below the flooding point to rise. So the differential pressure across the column will increase. Also, since heat from the reboiler is basically blocked from rising, the temperature at the bottom of the column may increase as well. As a result, there may be a greater differential temperature across the column. Now, if puking develops, the surge of liquid and vapor up and down the column can cause fluctuations in the pressures and temperatures, as well as in the level of liquid in the bottom of the column. Also, liquid that's forced out of the top of the column can cause a sudden rise in the level in the receiver. Now, some of the more common methods used to eliminate a flooding problem involve temporarily decreasing the feed rate, the reflux rate, or both to reduce the amount of liquid in the column, and decreasing the bottom temperature to reduce the flow rate of vapor up the column. In extreme cases, it may even be necessary to shut down the column so that the problem can be corrected. If the feed rate to a distillation column is too high, overloading and flooding can occur. But the performance of a distillation system can also suffer if the feed rate is too low. For example, if the feed rate to the column in this system decreases, the level of condensed overhead vapor in the receiver and the level of liquid in the bottom of the column will start to drop. As a result, less liquid will be available for reflux and for circulating through the reboiler. If the levels continue to fall, control devices will reduce the takeoff of overhead product and bottoms product. To correct a low feed rate problem, the cause of the problem has to be identified. If a feed line blockage is detected, it must be cleaned out so that the feed rate can be restored to normal. If an instrument reading seems unusual, it should be reported. In the meantime, the feed rate may have to be controlled manually. In addition to feed rate problems, feed temperature problems can also affect some distillation systems. For example, the temperature of the feed entering this column should be close to the temperature at the feed tray. If the temperature of the feed is much higher or lower than the temperature at the feed tray, product separation will be disturbed. Problems can also occur if the feed mixture is contaminated with water or other foreign material. Depending on the temperatures in the column, water could vaporize and contaminate the overhead product, or settle to the bottom of the column and contaminate the bottoms product. Many of the problems that affect a distillation system can occur during startup. For that reason, operators should be on the lookout for problems such as improper feed rates and temperatures, instrument failures, and residue buildup in feed and product lines. In vacuum distillation systems, operators should also watch for leaks. A vacuum leak will cause changes in the temperatures and pressures in the column, which can reduce the efficiency of the system or stop the distillation process altogether. The feed rate is the rate at which feed mixture is pumped to a column. The flow of feed to a column can affect the quantity and quality of overhead product and bottoms product. For that reason, an optimum feed rate is normally determined mathematically based on system equipment and the materials being processed. If a system's feed rate is too high, overloading can occur. Overloading is a condition in which the vapor rising up a column is impeded by the liquid flowing down the column. If the feed rate to a distillation column is too high, overloading and flooding can occur. But the performance of a distillation system can also suffer if the feed rate is too low. For example, if the feed rate to the column in this system decreases, the level of condensed overhead vapor in the receiver and the level of liquid in the bottom of the column will start to drop. As a result, less liquid will be available for reflux and for circulating through the reboiler. In a typical distillation system, overhead vapor from the column flows to a condenser where it's cooled and turned back into a liquid. In this system, the condensed liquid collects in a tank called a receiver. During startup, all of the condensed liquid is pumped back to the top of the column as reflux. Reflux cools the top of the column to keep it within a specified temperature range. It also helps condense heavier fractions that may have vaporized to improve the separation of bottoms product and overhead product. Once the system is operating normally, only part of the liquid is returned as reflux. The remainder is routed to overhead product storage. The ratio of the amount of liquid that's returned to the column as reflux to the amount that's sent to overhead storage is known as the reflux ratio. For example, if 4 times as much liquid is returned to the column as is sent to overhead storage, the reflux ratio is 4:1. The more liquid that's returned to a column, the greater the reflux ratio. Whether a reflux ratio is high or low depends on the design of the column and the mixture that's being distilled. For example, this mixture is made up of components that are hard to separate. A mixture whose components are hard to separate generally requires a high reflux ratio. On the other hand, a mixture whose components are easier to separate generally requires a lower reflux ratio. Maintaining the proper reflux ratio for a system is important because it can affect the equilibrium between the rising vapor and the falling liquid in the column. If that equilibrium is upset, the performance of the column will suffer. In this system, the reflux flow is regulated by a temperature controller that adjusts a valve in the reflux line. If the reflux rate is too high, too much liquid will flow down the column, and the top of the column will be cooled too much. As a result, too much vapor will condense before it reaches the top of the column, and the column could flood. Now, if the reflux rate is too low, there won't be enough liquid to flow down the column or to cool the top of the column properly. This could disrupt product separation. For example, heavier uncondensed vapor could rise up the column, mix with the overhead vapor, and be carried into the overhead condenser. In a distillation system, a condenser removes heat from the overhead vapor and turns the vapor back into a liquid. Two common types of condensers are water-cooled shell and tube condensers and air-cooled or fin fan condensers. Both types of condensers can experience problems. Many condenser problems are related to the cooling medium that flows through the condenser. These types of problems can ultimately affect the amount of cooling provided by the reflux. For example, if the cooling water flow through this shell and tube condenser is lower than normal, or if the water temperature is higher than normal, the temperature of the reflux may increase. As a result, less cooling could occur in the top of the column. This could cause heavier uncondensed vapor to rise too far up the column, mix with the overhead vapor, and be carried into the overhead condenser. Some common conditions that can reduce the cooling water flow through a shell and tube condenser are improper valve settings, problems with the cooling water pump, and deposits in the condenser tubes caused by impurities in the cooling water. In a fin fan condenser, the cooling medium is air. One of the main problems that can reduce the flow of air through a fin fan condenser is a problem with the fans. Also, some fin fan condensers have louvers to help control airflow. In these condensers, airflow can be reduced if the louvers stick in the wrong position. The ratio of the amount of liquid that's returned to the column as reflux to the amount that's sent to overhead storage is known as the reflux ratio. For example, if 4 times as much liquid is returned to the column as is sent to overhead storage, the reflux ratio is 4:1. Some common conditions that can reduce the cooling water flow through a shell and tube condenser are improper valve settings, problems with the cooling water pump, and deposits in the condenser tubes caused by impurities in the cooling water. Most distillation systems use some type of reboiler as the main source of heat input to the column. Two types of reboilers are shell and tube reboilers and reboiler furnaces or fired reboilers. In a typical fired reboiler, oil or gas is burned in a furnace to heat the bottom's liquid that's pumped through the reboiler and back into the column. A temperature controller regulates the amount of heat input to the column by adjusting the fuel flow to the reboiler. In a shell and tube reboiler, steam is often the heating medium. The steam flows through tubes inside the reboiler, while liquid from the bottom of the column flows around the tubes through the shell of the reboiler. A temperature controller regulates the heat input to the column by signaling a control valve to adjust the steam flow to the reboiler. Changes in the steam flow to a shell and tube reboiler will affect the amount of vapor going up the column. To avoid upsetting the equilibrium between the rising vapor and the falling liquid in the column, changes in reboiler operation should be made gradually. If the reboiler in a distillation system isn't operated correctly, problems can occur and the distillation process can suffer. For example, the shell and tube reboiler represented here must be started up a certain way to prevent damage and product contamination. A pump is used to circulate bottoms mixture through the reboiler. So this is a forced circulation system. The heating medium for the reboiler is steam. The steam flows through the tube side of the reboiler and transfers heat to the mixture flowing through the shell side of the reboiler. During the startup of this reboiler, before any steam is supplied, the reboiler must be full of circulating mixture. So there has to be a sufficient level of mixture in the column, and the reboiler circulating pump must be running. In this system, circulating the mixture prevents it from overheating once steam is supplied to the reboiler. If some mixtures overheat, they can bake onto the reboiler tubes, fouling the tubes and restricting the heat transfer from the steam to the mixture. Once the reboiler is ready to receive steam, the steam should be supplied gradually. If steam is supplied too quickly, the tubes in the reboiler could expand unevenly and possibly crack. If the column pressure is greater than the pressure in the steam system, some of the mixture could contaminate the steam system and damage it. If the column pressure is less than the pressure in the steam system, steam could leak out and contaminate the mixture flowing back to the column. Supplying steam to the reboiler too quickly can also cause the lighter component in the mixture to vaporize too rapidly. If that happens, the expanding vapor could rush up the column and possibly damage the internal structures of the column. Now, fired reboilers can experience some of the same problems as shell and tube reboilers, including tube fouling and tube leaks. But since fired reboilers burn fuel to heat the bottom's liquid, they sometimes experience combustion problems as well. For example, too little airflow can cause incomplete combustion in the furnace. As a result, more than the necessary amount of fuel is burned to maintain the temperature in the bottom of the column at set point. To prevent these types of problems from occurring, operators should follow their plant's procedures for operating reboilers. Distillation systems use a lot of energy. The key to maximizing efficiency is to produce on-spec products with the least amount of energy consumption. One problem that can interfere with efficient operation is overfractionation. Overfractionation results in the excessive use of steam and other utilities to produce products. Simply put, it involves using more heating and cooling than necessary. One way overfractionation can occur is when the differential temperature in a column becomes too great. For example, if the bottom temperature is higher than necessary for product separation, more hot vapor will rise up the column. To adjust for the increase in temperature, the control system will increase the reflux flow rate. If the cooling effect of the increased reflux offsets the rise in bottom temperature, the system may reach a new set of steady-state conditions. Under these conditions, product composition may still be within specs, but a lot more energy will be used to produce basically the same products. By lowering the temperature at the bottom of the column to its proper value, the overfractionation problem can be eliminated, and the column can return to its original operating conditions. In a shell and tube reboiler, steam is often the heating medium. The steam flows through tubes inside the reboiler, while liquid from the bottom of the column flows around the tubes through the shell of the reboiler. A temperature controller regulates the heat input to the column by signaling a control valve to adjust the steam flow to the reboiler. Now, fired reboilers can experience some of the same problems as shell and tube reboilers, including tube fouling and tube leaks. But since fired reboilers burn fuel to heat the bottom's liquid, they sometimes experience combustion problems as well. For example, too little airflow can cause incomplete combustion in the furnace. As a result, more than the necessary amount of fuel is burned to maintain the temperature in the bottom of the column at set point. One problem that can interfere with efficient operation is overfractionation. Overfractionation results in the excessive use of steam and other utilities to produce products. Simply put, it involves using more heating and cooling than necessary.